To open today's session, it's a privilege to welcome a very esteemed guest, Professor Aditi Sen. Professor Sen is a leading figure in quantum information and computation, currently based at the Harish Chandra Research Institute. Her research spans quantum communication, entanglement theory, cryptography, and many body physics. With over 100 publications and global collaborations to her name, she brings a wealth of knowledge and experience. She completed her PhD at the University of Gdansk, Poland, and has held prestigious fellowships in Germany and Spain. In 2018, she became the first woman physicist to receive the Shanti Swarup Bhatnagar Prize and was most recently honored with the G.D. Birla Award for Scientific Excellence in 2023. Professor Sende is a fellow of both the Indian Academy of Sciences and Indian National Science Academy. Please join me in warmly welcoming Professor Aditi Sen for her keynote address. We are excited to hear from you, ma'am.
Okay, thank you very much.
Thank you, Aditi.
Thanks, Tri. Thank you, the organizers, for inviting me and also for kind introduction. So I share the screen. Is it visible? Hello? Can you see my screen?
Yes, ma'am.
Okay. And also my voice is clear, right?
Yes, ma'am, the voice is clear.
Okay, so I start. So today, actually, I have three lectures. So I will be talking about quantum communication networks. So mostly, I will talk about the quantum communication protocols, and also briefly I will talk about that how these protocols can be extended to quantum communication to build quantum communication networks, which in other words also called quantum internet nowadays. This is one of the exciting area of research. There are many open problems when we talk about to build quantum communication networks or internet. And it's also one of the experimental challenges that currently we are facing. So I will briefly touch about the networks, but mostly I will concentrate on quantum communication. So as we know, we are very aware of many communication devices, and interestingly, we are also, now talking to each other with the help of only a very good communication devices like internet. And so every day we use several communication devices like internet, mobile phone to connect each other, and much more sophisticated one nowadays. And we know that the usefulness or the advantages that we can get by using communication devices. And I think that this audience doesn't require that much emphasis of what are the usefulness of communication devices. And this is not only true that today we were using communication devices, but communication are useful that we know from old time. So whether we use pigeon or even a few years back, the communication or the information that we can gather via reading newspaper, or when we want to send some messages, we used Indian Post, for example, to send letters. So there are many ways people have tried over the years or over the centuries that how to communicate between each other. And so today we will be talking about only these kind of devices which actually can enhance the connectivity between all of us. So, as I have already mentioned, there are already a kind of revolution in communication devices that we can see. So, for example, this is probably when I was small, and when we used to have these kind of devices, where we used to write letters to send information to our friends, relatives, and so on. But nowadays, probably in this era, we don't send letters via post, but we just send email or SMS or WhatsApp or some e-message we use. So there is already a kind of communication devices revolution that has happened, that is due to the enhancement, or that due to the development of electronics. Uh, Now, what are the basic steps or what we need in communication? So, as we can understand that in any communication protocol that we will be interested in, that at least require two parties or more. So we whenever we are talking about communication or sending information from one place to another, then that should involve at least two parties, and one is a sender, another is a receiver. Now, sender, typically we call it Alice, and the receiver we call it Bob. And importantly, they are situated in two distant locations. So, for example, sender can be in Shilchar and receiver can be in the Allahabad. It can be even in two continents. So, the important point here to stress that sender and receiver are situated in two distant locations. A process, so communication is a process by which informations can be sent from a sender to a receiver via some medium. Now, there are certain steps that in all the communications that even today we are currently doing.
Excuse me,
Yes,
ma'am.
yes.
Ma'am, we can see your screen, but we cannot see the presentation.
Oh, so up to now you haven't seen the presentation?
No, no, no.
Oh, that's bad. Okay, oh, sorry. Can you now see?
No, ma'am.
Okay, just a minute. There are some issues. Now
Yes, ma'am.
Yes, ma'am.
you can see. Okay, sorry.
Yes, it is
Uh,
visible.
so can you see the changes?
Yes, ma'am.
Okay.
Yes, yes, ma'am.
Okay. Should I start from the beginning? Although I haven't shown much, but yeah. So as I said that I will be talking about quantum communication network. So the thing that now you can see the screen.
Yes, ma'am.
Okay. Okay. So as I was telling that we have already, we are using the current communication devices, which include mobile phone, internet, etc., and to connect each other. And this is going on for a long time because it will be, I mean, century ago, it can be between by using pigeons, or we use just newspapers or post office to, or any kind of companies to send letters or informations, or to send certain parcels from one place to another. So as I was kind of emphasizing that there is already a revolution in communication. So here are probably when I was young, maybe 40, 50 years ago, and this is a current scenario where we are using more electronic based communication devices. And so, whatever today we will be discussing, we will try to compare that with the devices that we are using currently. So we have to somehow show in my next today and next two talks that whatever communication devices that we are using, we can enhance their performances by using quantum mechanics. And that's the goal in this talk. So, as I said, communication requires at least two parties. And they should be, one is the sender, another is the receiver. Sender, I call it Alice. Receiver, I call it Bob. And importantly, they are situated in two distant locations. I hope now the screens are visible.
Yes, ma'am.
Okay. And you see the changes, right?
Yes, ma'am.
Okay. So now I think I was showing two photos of the actors. I hope you can recognize them. Uh, so, and they are situated in two distant locations. So, as I said, that they can be, one can be in Shilchar, another can be in Allahabad, but they can be in any two locations. Can be situated in two different continents. So communication is a process by which information can be sent from a sender to a receiver via some medium. So, uh, what are the steps typically followed in any communication protocol? One is the sender encodes the message, and because sender wants to send some information to the receiver, and information, according to Landau, information is physical. What do you mean by information is physical? That means information must be encoded in and decoded from a physical system. Now, these physical systems in a classical world can be something like red green balls, signs of a charge of a particle, different kinds of waves, different kinds of frequency of light, and so on. But most importantly, in a classical world, whatever the devices that we are using now, only contains orthogonal states. That means they are distinguishable objects. Although the distinguishability can be different, can be difficult due to the lack of our knowledge, but typically the encoding or the decoding should occur with the help of physical systems which are in orthogonal states or distinguishable objects. On the other hand, in a quantum world, we know that there are orthogonal states as well as non-orthogonal states. So this information must be encoded in and decoded from a physical system, which can be non-orthogonal as well as orthogonal. So they can be either distinguishable states or indistinguishable objects. So as we can see that quantum world contain more kind of states, and so there is already a hope that quantum, by using quantum mechanics, if we can build certain devices that can enhance the information transmission capability of us, I mean capability for us. And so uh, under this hope, people try to explore. But before I go that, so just to tell you that what do I mean by encoding in a physical system? So you can think that I want to send, suppose that I am currently in Hyderabad. Okay, so this instead of saying Hyderabad, I will send this. And so if you can see that this is H is encoded as K. So if you see, so this is, instead of sending H, I actually move 3 steps forward in alphabet. So H will be IJK, Y will be similarly B, D will be EFG, and so on. So I, instead of sending Hyderabad, I will send this message to the receiver. So this is one kind of encoding. There can be much more sophisticated kind of encoding, and so on. So I will talk about that in all my talks, that how to encode information to send that to the receiver. Yes? Hello? Okay. So after encoding the information, one has to send it to the receiver, and for that you actually require certain medium. So as I kind of showing that long back when we Alice encodes the information, they probably use horse rider to send the information from one place to another. And currently we use optical fiber, for example, to send information from one place to another. So we require encoding, we require sending medium, and then the Bob receives a message and Bob should decode the message. So Bob, as I have said, that instead of Hyderabad, Alice sends this, and Bob should know how to decode the message. So Bob can receive the message with the help of the sending medium, and then Bob can decode the message according to certain rule that Alice or Bob are using. So these are the three steps that are important in any communication protocol. Now, the question that we are going to ask in this talk, that is this encoding, sending, and decoding. These are the three steps in any communication protocol. Can that be enhanced, or can quantum mechanics help us to enhance the capability of sending information from one place to another? And that is the goal of my talk, to convince you that yes, indeed, it is possible to enhance the capability of sending information from one place to another with the help of quantum mechanics, quantum mechanical principles. And the question that I will be trying to answer in today's talk and the Monday and Tuesday's talk, how and why we want to use that. So, more or less, the outline of my talk will be communications, and the first two lectures will be on communication, where there will be no security aspect. That means Alice wants to send certain information to Bob, and but Alice doesn't want to send the information in such a way that there will be no third party. There is no restriction. The third party cannot gather this information. So this you can think, for example, in a situation, suppose I am talking with you now, and now suppose there will be a third party who is not supposed to join in this lecture, uh, is listening this talk, but there is no harm that he or she is listening this talk, or they are listening this talk. And suppose when we are talking with our friend, or we are relative, with our mother, with our father, and then there can be a possibility that another person somehow is present in the line and also hearing our talk. Now, this can be embarrassing, but it is not really leaking any information, or it is not really any harm. So, this is what I mean by communication without security. So, first two lectures, I will talk about communication protocols where there will be no security issue. And first lecture, today's lecture, I will be talking about how quantum mechanics help to send classical information from one place to another. And the second lectures, I will talk about quantum state transfer protocol. And the third one, which actually is one of the important direction of in the communication protocols, is a secure communication. So classical cryptography is a very advanced subject, but I will be talking in my last lecture how quantum mechanics help to enhance cryptographic protocols in this world. So this is how I will be dividing my lectures. So today I will be, as I said, I will be discussing about classical information transmissions with the help of quantum states. So there are, I know that the audience is aware of quantum mechanics, but the basic two three things that I will use in my talk. So I will just briefly discuss. So situations in a physical system that I want to describe can be represented by a vectors in a linear space with an angle defined. And that what do I mean by that? That means this is a Hilbert space. So any situations in a physical system correspond to an element in a Hilbert space. And with this, we can actually define something called qubit or quantum bit. So QU for quantum and bit is for bit. So quantum bit is similar to the classical bit. What is classical bit? This is a basic unit in classical computer. Classical computer means the computer that we are using nowadays, all the desktop, laptops, workstations, etc. And there, the basic unit which we use is bit, that is one of the zeros and one. Now, the basic unit, what we will be going to build, if we are able to build quantum computer, is the qubit, which is quantum bit. And what is that? This is just an superpositions, arbitrary superpositions of two orthogonal states. So here I use spin degrees of freedom. So up spin is in the, you can think of an eigenvector of sigma z, the Pauli matrix, and downspin is the eigenvector of sigma z of the Pauli matrix. It can be any two orthogonal states as well. And alpha beta are complex number, and in quantum mechanics we know that they should be normalized, and so mod alpha square plus mod beta square is equal to 1. Now, similar to classical bit, actually these two states, up and down, are orthogonal states, and that's why we can always rewrite or always represents that as 0 and 1. So this we just writing because we want to a similar kind of analogous situation like in a classical computer. And so this will be, we can denote this up as 0, down as 1. And so phi, the arbitrary state in or any qubit, can be represented as alpha 0 plus beta 1 with alpha beta complex number, and this is the normalization condition. Now, this can also be represented as, or analogously, it can be represented as the points of the surface of the sphere, where the poles represents the up or down spin, that means zeros and one, and all the points on the surface of the sphere represents a qubit. So as you can already see that in a classical world, since the orthogonal states exist, only the poles exist. On the other hand, in the sphere, the surface of the sphere contains infinite number of points, and they all represents a qubit. So qubit is an arbitrary element in two-dimensional complex Hilbert space, and so this can be geometrically or kind of can be represented as the points in the surface of the sphere. But here we just I want to stress that this surface of the sphere is just a kind of analogous way to represent qubit. It's not really surface of the sphere, because this is the surface of the sphere means it's a three-dimensional system, real. But here we are talking about Hilbert space and with complex numbers and so on. So this is not just a analogous way to represent. Now, there are another things that I will be using in my whole talk is, so if we think about solids, that can be sometimes be represented as arrays of electron spin. And in quantum mechanics, it can be represented as a tensor product of several Hilbert space. So as a several Hilbert space mean complex Hilbert space. And so that can be represented as C1 tensor, C2 tensor, so on. So there are many spins, then this will go on. So suppose in a solids, the spins are aligned like up, up, down. Then this can be represented as up tensor product, down, and so on. So in my talk, I will be using this tensor product Hilbert space again and again to explain certain things, and so that's why I put it. Probably it's just this audience may not need this understanding. Now, another important concepts that I will be using is quantum measurement. So, typically there is a source which is producing a quantum state psi, and then there is a measurement black box, you can think. This measurement is performing a measurement, say, in the up-down basis. So, these two are orthogonal states. Then the finding up state or and there are two kind of path in which it can be the state can come out, and uh, and the probability of obtaining up state is up size inner product modular square, and this is the Born rule that we will be using again in my talk. And this you can think as a this probability is just like in tossing a coin. uh, we are not talking biased or not, and the probability is, as I said, that if source is sending psi and I am performing measurement in up down basis or any arbitrary basis, say phi, then the Bond rule tells us that obtaining phi is the probability of obtaining phi is equal to phi psi modulus, inner product modulus square. So this also we will be using in my talk. Now, before I present the communication protocol, I just want to say that to run a car, we require fuel. So it can be petrol, it can be diesel, it can be CNG gas or something. Now, similarly, to make our food, at least the Indian food, tasty, we require spice. So without spice, it's not very tasty, at least in India. And so we require this fuel or spices to run the car or to make the food tasty. Similarly, in all these communication protocol, we also require some basic ingredient. And that basic ingredient is known as something called entanglement, which is a property of quantum state, which are quantum state shared between at least two parties. So, as I have already told you, that in any communication protocol, we require at least two parties. So, the resource or the fuel that we require is also between two parties. It can be more as well, and as I will show, that it can be more difficult when we want to actually consider the communication protocol involving many or multiple parties. So, if you are interested to learn theory of entanglement, there is a nice review article by Horodetzky in 2009, which is old, but still it's quite complete in a sense that the basic idea you can gather from this review article. Now, let me define that what is entanglement. So again, as I said, entanglement can be defined between many parties, but today I will be concentrating only two parties. So there are Alice and Bob. They are situated in two distant locations, and the useless or unentangled states are those states that Alice and Bob can prepare even when they are situated in two distant locations. So, mathematically speaking, Alice prepares a quantum mechanical state phi A and Bob prepares a quantum mechanical state phi B. Then the joint state, as I have mentioned, is written like phi A tensor product phi B. And these states are the useless states in communication protocol and in many quantum information processing protocol that you will learn over this workshop. Yes? Any question? Hello? Can you hear me?
Yes, ma'am, you're audible.
Okay, okay. And the slides are going right?
Yes, ma'am.
Okay. Okay, so this is the unentangled or useless states, which are actually Alice and Bob can prepare even when they are situated in two distant locations. So good examples can be this. So Alice prepares a up spin Bob prepares the upspin, and similarly, Alice prepares the upspin, Bob prepares the downspin, and so on. So this is, they are not, suppose you are not talking, Alice and Bob are not talking. Just Alice is doing some experiment in her lab and Bob is doing another experiment in his lab. So these are two isolated thing going on. And this is kind of isolated preparation procedure going on. And these are the unentangled or useless states. On the other hand, entangled states and the useful states in our case in communication protocol, and as I said in many quantum information protocol, that the entangled states are those states that Alice and Bob are unable to prepare when they are situated in two distant locations. So you can think of mathematically, so the entangled states are those states when the state phi AB, the joint state cannot be written as phi A tensor product phi B. And these states are mathematically called the entangled states, and they will be useful for communication and quantum information protocols. And so the good example is the singlet state. So this probably we have all seen. So here up spin tensor product down minus down spin tensor product up. And in quantum information, we typically this also we call the Bell state. And now you can ask that how can we prepare then this state which can be shared between Alice and Bob. So an example can be, or preparation procedure can be as follows, that there will be a source, suppose source is situated in Delhi. So source prepares an entangled state and then source sends one particle to Alice, say in Allahabad, and another particle to Hyderabad, so where the Bob is situated. Suppose I want, who I am situated in Allahabad, so I want to do certain communication or certain information protocol between Bob or the receiver who is situated in Hyderabad. And so Delhi, there will be a source which prepares this entangled state, sends one particle to Alice, another particle to Bob, who are situated in two distant locations. And this is the only way Alice and Bob can prepare these entangled states when they are situated in two distant locations. Now, there is another possibility that the source is with Alice. And so Alice can prepare an entangled state, keep one particle with her, another particle Alice sends to Bob, who is situated in distant location. So either Alice is the boss of the communication, company, or Alice and Bob both can use certain communication company who will now distribute this entangled state between distant locations. So that is the idea that in some years later we are expecting. Okay, so as I said that here, just like a bridge which connects two sides of the river, similarly, entangled state actually connects the two people, like sender and the receiver, and these entangled state will be shared between sender and receiver, which will be used to execute certain communication protocols. So these quantum bridge or these useful states are extremely useful, not only for communications, but also in metrology or quantum sensing. It can be also useful in some computational tasks and many quantum information protocols that you will be listening in probably in this workshop. Now, although this definition looks so simple, because as I said that when the state can be written as phi A tensor product phi B, then this is a useless state, and the states which can be cannot be written like phi A tensor product phi B, they are the entangled states. However, and these definitions can be modified when I go to a density matrix formalism, which I am not using here. So that means an arbitrary state. The definition remains almost similar, but it has to be modified accordingly. But the definition can be given easily. Now, although the definition is so simple, but still it is an open question that given a quantum state, how to detect entangled states in laboratory as well as in theoretically. So this we still don't know an efficient entanglement criteria or entanglement detection method by which one can detect or one can establish whether a given state is entangled or not. So this is one of the open questions in this field. Now, in case of two party, the things are quite sorted and it's known, or there are methods which are known, which are quite efficiently can be applied. But in a multipartite or when there are many parties which share entangled state, this method is completely unknown, and it's one of the challenging area in quantum information. So I just want to tell you that just like so finding or detecting entangled state means that making a very good or finer nets to catch the fish. So when the main problem of detecting entangled state is that typically in there are a possibility to create very highly entangled state. At the same time, there is a possibility to create a weakly entangled state in experimentally. And so creating a finer net to catch the smaller fish is difficult, that we know from our experience. And so creating a good entanglement criteria which can detect all entangled states that can be prepared experimentally is difficult. So this picture was actually we have used in one of our review article uh, on other quantum correlation or other type of resource theory, like other fuels that you require to build quantum information protocol. And this was drawn by one of our master thesis student. Now, I mean, just to emphasize that this is the question of detecting entangled state is difficult, and this was recognized by Nobel Prize in Physics in 2022 when it was awarded to Alain Aspect, John F. Clauser, and Anton Zeilinger. As it was mentioned in the Nobel by the Nobel Committee, that this was recognized for experiments with entangled photon. So they have created entangled photons, but importantly they have established the photons are entangled by the violation of Bell inequalities, and that's kind of starting point of quantum information science or quantum communication. So as I was trying to tell you that creating entangled photon is one step, but after creation of entangled photon, more important thing is to establish that really the photons are entangled. And to establish, you require a detection criteria. One of the detection criteria is violation of Bell inequalities that they have used to establish or to certify that the state is entangled. Now, this they have done when there are two parties. Now it is even become quite difficult when there are multiple parties to certify that the state is entangled. So this is one of the ongoing research in quantum information science. Okay, so now with this kind of preliminary of entangled states, we actually talk about how to really improve our communication or information sending capability by using quantum mechanics. So today I will be going to discuss about a protocol which is quantum dense coding. So I have another half an hour. So I will be discussing about a work by Charles Bennett and Weisner. This is Charles Bennett. Actually, the photo is taken when he was at HRI. And Weisner, this paper was published in Physical Review Letters 1992. So suppose first I discuss about a classical protocol before going to a quantum one. So suppose Alice wants to send the informations about the weather uh, in her place to Bob. It can have many possibilities. So you can encode these informations in several ways. So suppose today is sunny, or it is windy, or snowing, or raining. So suppose there are four possibilities, and Alice wants to send one of them. So Alice wakes up in the morning, find out the weather, and depending on the weather situation, Alice sends the information to Bob. So this is the goal. So this is actually this. There are four options, and so that means the 2 bits. So there are four distinguishable objects or four distinguishable situations that Alice wants to send, and that means log of base to 4, and that means 2 bits of information that Alice wants to send to Bob. So if you have n distinguishable object, then this will be log of n. Typically in this information, as I said, that classical information is always or in a classical encoding in bits. That means there are two options, 0 or 1, and that's why the base of log are always taken to be 2. And so there are four distinguishable objects, and so this is log base to 4, and that's why it's a 2 bits of information that Alice wants to send. How Alice performs the encoding? Alice, as I said, that this is a 2 bits of information. So if it is sunny, Alice wants to send 0, 0. If it's snowy, 0, 1, windy, 1, 0, and 1, 1. So how she can encode in a classical protocol? Alice can use different colors of balls, say blue ball for sunny, snowing, then the yellow, windy, then this is gray, and if it is raining, then green ball. Instead of balls, Alice can use different colors of the flowers, and Alice can encode in a similar fashion. So if it is snowing, so in the morning Alice finds that it is raining, then Alice sends the green ball or the green color flower to Bob. Now that sending will be done by certain medium. So in the classical protocol, you can think that Alice, if Alice wants to send the green color flower to Bob, then Alice buys this green color flower and go to the DTDC and send it to Bob. So there will be some sending way, sending method, sending medium by which Alice has to send. And now Bob can easily decode the message because these four options are distinguishable, are encoded in such a way that they are distinguishable by color. So if Bob finds that Alice has sent the green color flower, then immediately Bob understands that today Alice's plate it is raining. If suppose Alice for Bob gets the blue color flower, then immediately Bob infers that today Alice's weather is sunny. So in this way, since you can distinguish all the options by a color, Bob can decode the message. So you can think that this is a very simple way to encode the message. But why should I use ball or flower? I can use a very sophisticated technique in case of in encoding. But since as I have told in the beginning, and we know that in a classical world, all the objects are distinguishable. So the only options to encode information is via orthogonal states. And orthogonal states means they are distinguishable objects. And so instead of using these colors of the balls or colors of the flowers, you can use much more sophisticated technique, but they all will be orthogonal and distinguishable. And so there cannot be any other method by which, one can do this. So in other words, to encode these 2 bits of classical information, Alice requires 4 distinguishable objects, and that means Alice requires 4 dimension. Now, if I have some system and I want to infer the dimension of the system, I have to find that how many orthogonal states that I can have in that dimension or in this system. And that actually tells us that, so the number of orthogonal states in that system can tell us what will be the dimension of the system. So in 4 dimension, there will be 4 orthogonal states. In 10 dimension, there will be 10 orthogonal states and so on. So the number of basis elements actually can tell us what will be the dimension of the system. So here, to send these 2 bits of classical information, Alice requires 4 dimension in a classical protocol. So now we are ready to go what we can do, how to improve by using quantum mechanics. Now, in a quantum world, as I have said, there can be an entangled state that can be shared between Alice and Bob. Suppose a priori, before starting of the protocol, Alice and Bob shares an entangled state, the singlet state that I have already discussed. So suppose Alice shares this entangled states, and Alice now wants to send these 2 bits of classical information, the same one which we have done in case of classical protocol. So what can Alice do? So Alice performs a unitary operator on her part of the system. So this is the unitary operator. We know the unitary operator is such that U dagger U is identity operator. And these are the examples of unitary operator. Identity operator is a unitary operator because I dagger I is of course I. One can easily check that the Pauli operator, Pauli matrices are all unitary operator. So sigma Z, sigma X, and sigma Y. So depending on the message that Alice wants to send, Alice performs one of the unitary operator on her part of the system. So if Alice finds in the morning that today it is sunny, then Alice performs the identity operator. If it is raining, Alice performs sigma Y operator on her part, and so on. And interestingly, you can check that if Alice performs the identity operator on her part, the singlet, the state remains as it is. If Alice applies sigma Z on her part, due to entanglement, the entire states actually become psi plus, which is the up, down plus, down up state. If it is windy, if Alice applies sigma X on her part, then it will be phi plus, that is up up plus down down, one of the triplet state. And if it is raining, that means if Alice applies sigma Y, then the state, so state becomes up up minus down down. So again, I want to stress, Alice is applying unitary operator, that is one of these Pauli operator, only on her part of the system. Due to the entanglement that I have discussed before, the entire state transforms to one of the state. So suppose Alice's weather today is windy. So then Alice performs a sigma X operator on her part, and that transforms the entire state to phi plus. And then Alice sends her particle to Bob. So Bob has both the particle, and Bob has to distinguish these 4 states. And just like a color of the ball, since quantum mechanics, we know that the orthogonal states can be distinguished by, for example, in a single system, we know that, and if we are talking about spin degrees of freedom, one can distinguish these orthogonal states by Stern-Gerlach experiment. Similarly, here this is a much more complicated composite system situation, and this is in 4 dimension. And this can also, you can also design a Stern-Gerlach type measurements by which one can distinguish these 4 states. So this is possible to distinguish, and hence can decode the message, and can understand or can infer what Alice has sent. So suppose Alice, as I said, suppose Bob realizes that the state that is after sending the Alice's part to Bob, the state is in phi minus. Immediately, Bob infers that today Alice's place it is raining. So if he finds that it is psi plus, then immediately he infers that in her place it is snowing, and so on. So similarly, as we have done in a classical protocol, we find that we can, just by using entangled state, you can transform these states. Hello. Hello. Okay, so these states to orthogonal states, and so these can be easily distinguishable. So Bob can decode the message. But here, importantly, as you see, that to do this, to encode these 2 bits of classical information, Alice only operates on her part of the system, and her part is 2-dimension. So Alice only encodes information in 2-dimensional system. So the moral of the entire story is the following, that here Alice actually, in the classical protocol, to encode information, Alice requires 4-dimensional space. On the other hand, to send these 2 bits or to encode these 2 bits of classical information in a quantum world by using entangled state, Alice only requires 2 dimension. So you see that already you can double the classical information sending capability by using the quantum systems like quantum entangled states. Now, in a more realistic scenario that I probably discuss in next few minutes that I have left. So typically, actually, Alice and Bob in experiment, it will not be a good situation that Alice and Bob shares and shares just maximally entangled states or this singlet state. But it will be something an arbitrary density matrix. Hello. Okay. So so Alice and Bob's share some states which will be an arbitrary density matrix. This can be entangled, but not as entangled as the previous one or the singlet or triplet. So although I haven't defined the entanglement measure or the how to quantify entanglement, but this will be something like I want to prepare singlet state, but I end up with singlet plus some noise, because noise is inevitable when we share entangled state. So as we have discussed, that source prepares some entangled state, or that and then sends one particle to Alice, another part to Bob. And when they will send, or source sends these 2 particles to Alice and Bob, they will use some medium, and that medium will be surely noisy. And so finally, Alice and Bob, who are situated in 2 distant locations, they share a state which will be a noisy entangled state. Now, in this situation, we can actually also kind of discuss this kind of dense coding protocol. So Alice's task is to send classical information I to Bob, and this I occurs with probability pi. This you can always infer. So for example, since I am in Prayagraj, all the weather reports that I have shown, there is hardly a possibility that it will be snowing. So the probability of snowing in Allahabad is almost 0, actually 0. On the other hand, and also if I am in summer, then the probability of raining in summer in Allahabad is also very low. On the other hand, if I am in Kolkata, then probability of having raining in Kolkata will be higher. So that is what I mean by sending classical information I with probability pi. So depending on the place, the weather condition changes, and so the probability of all these possibilities also changes. And so there will be some have more probability, some have less probability, and so on. Now, depending on the information I, Alice performs a unitary operator that I have already mentioned, and depending on this information, classical information I, Alice actually applies a unitary operator I on her part of the system, and if you apply unitary operator on the shared state, you finally creates a states which are pi rho I a b. And then, as I said, so in case of rho ab is singlet, we have already seen these rho I a b, the states that will be created after the unitary operator will be all four orthogonal states. On the other hand, if Alice and Bob share some other states, not the singlet state, but some noisy state, these rho I a b may not be orthogonal. And that means when Alice sends her part to Bob, Bob will not be able to gather the entire information that Alice has sent. And this was actually kind of solved by us long back in 2004, and also by T. Hiroshima in 2001, Zeman and Buzek in 2003, and so on. So this question was, so here when the Alice and Bob share an arbitrary quantum state, that means a noisy state, then what will be the dense coding capacity was solved in this work. So as I said, again I repeat that depending on the message I, Alice performs unitary operator ui, create the states pi rho I a b, and then Alice sends her part of the system through a noiseless channel to Bob. So Bob has both the particles since they are no more orthogonal states. So, but still Bob can perform certain measurements, because in quantum mechanics, only way to gather information is via measurement. So Bob has to perform certain measurement to gather as much information as possible about I from the ensemble this. And this actually can be done, and there are some bound which can be used, and by using that bound, we found that the dense coding capacity actually takes this mathematical form. Now, I just discuss not in detail about this mathematical expression, but just to tell you that if Alice's dimension is dA, then classically Alice can send only log dA bits. On the other hand, if Alice and Bob share some entangled state, then Alice can send log dA plus this amount of information to Bob. And this information can be positive in general, where this S is the von Neumann entropy, which is defined like that. And when sigma is written in a spectral decomposition, this reduces to the Shannon entropy, which we learn in a statistical mechanics course. And rho B is the local Bob subsystem, and rho AB is the total system. So in this way, you can see that this will be the Alice information that Alice will be able to sense when there will be no entangled state share. Alice can improve the classical information capability by this much of amount when they share an entangled state. So in other words, a state is said to be advantageous or beneficial for quantum dense coding protocol if S of rho B minus S of rho AB is greater than 0. And indeed, there are states for which it can be greater than 0. So for all PO state, this is actually 0. And so S of rho B is always greater than 0 for entangled state in case of pure. So all pure entangled states are useful for dense coding. Pure two-party entangled states are useful for dense coding, and that was shown. But in case of mixed state, there are mixed states which are useful for dense coding. At the same time, there are some noisy mixed states or noisy density matrix which are not useful for dense coding. If you are also interested to get the kind of review article that myself and Ujjwal was written in 2010, which are also available in archive. This From this you can actually it is written in for students, but this is a kind of review article of all the quantum communication protocols that I will be discussing in 3 lectures. Now, as I have said, that finally we want to find a dense coding network. That means it's kind of many senders and possibly multiple receivers. But let's first consider the scenario where there are n senders and a single receiver. Now, this problem I'm not going to discuss because this is another mathematically involved problem, and but this problem can be solved. So, if there are n number of senders and a single receiver share an entangled multipartite entangled state, then similarly dense coding protocol can be designed. And not only that, but when they share an arbitrary density matrix, that means noisy state, then also dense coding capacity can be found. And this was actually looks like that. I'm not going to explain this, but again, I just want to say this is the quantum advantage that you get, and this is the classical part or the classical capacity. So this problem is we have done extensive research in last 10 years or so. So this is one of my students, Tomongno's thesis in 2017. He is currently a faculty in IIT Kharagpur, and so he considers that how we can have a dense coding network in a multiple sender and a receiver scenario when there is noise. So I just here kind of noted down what are the problems in this area are solved, what are not solved. So I have discussed very extensively the original dense coding protocol where there is a single sender and a single receiver. And when the sender sends her qubit to Bob via noiseless quantum channel. Now, initial protocol considers when the sender and receiver share a singlet state, which is the original protocol by Bennett and Weisner in 1992. As I have said, when there is a arbitrary state shared, then dense coding capacity is known, and this is known in a community. Now, for last 20 years or so, now in the case of when there is a single sender and single receiver, the shared state is noisy, and after encoding, the state that Alice sent to Bob is also through a noisy channel. Then the problem becomes much more complicated, and then dense coding capacity is only partially known, even when there is a single sender and a single receiver. So there are two noise in this picture, two layers of noise. One is when sender and receiver share a noisy state, which is the initial state. After that, sender performs certain unitary operator, that means this kind of encoding, and sends her part of the system to Bob. And when sending her part of the system through a noiseless channel or not, this is important. So as I have shown you here, this. So Alice encodes via unitary operator, sends her part via noiseless quantum channel, so that Alice and Bob, or the Bob receives this two particle state, which will be exactly same as the state that Alice created after encoding. So for example, if I think about the original protocol, then as I said, that after this unitary operator, this sigma x, sigma y that we have discussed in detail, Alice creates these four orthogonal states. Now, we assume in the entire protocol when we discuss in the beginning that all these states are sent to Bob, and the Bob exactly got these four orthogonal states, and so he can decode the message. But if the sending part Alice uses, or Alice and Bob uses a noiseless quantum channel, then only the exact state will be sent. Instead of this noiseless channel, if Alice or Bob uses a noisy channel, then the exact this pi rho I AB that Alice has created via this unitary operator will not be received by Bob, and so then this will be some kind of rho I prime. And this situation is much more complicated and it's not yet solved uh, totally, even for a single sender and a single receiver case. When there is a n senders, one receiver, again the noiseless scenario after encoding is solved. This is known. Noisy case, again, it is not known. Now the things become very complicated when there are, instead of single receiver, there are two receivers or more. And this part, hardly the results are known. And there are several open questions, and partially we have solved certain problems in this regime, but there are many unsolved problems there, and which are really mathematically complicated, and it's not at all easy to solve. So for example, in the at HRI we are trying this for a long time, and we have some partial results, but still it's mathematically very involved, and it's not very easy to solve. So it's people are trying over the world for last 20 years but not able to solve this problem. Now, the next maybe 10 minutes, I will briefly discuss about the experiments. So, up to now, all the protocols that I have discussed is actually a theoretical dense coding protocol. So, it's a natural question that whether the people have done the experiment or not. Because in physics, it's incomplete without experiment. And so, there will be whether this dense coding protocol that I have discussed, people have done it experimentally. So the first experiment was done by Anton Zeilinger group in 1996, where they have developed a dense coding protocol experimentally by using photons. Now, in this case of photons, they have used polarization degrees of freedom of photon, and this is their more or less the table that photonic table that they have used. So there are some BBO crystal that they use to create an entangled state. So there is a UP pump that actually pulls the BBO. It was kind of pump on the BBO crystal, which create an entangled state. And after that, they have done all this encoding and decoding part. So as you see that this is the Alice's part, this is the Bob part. So the encoding is done in the Alice's part and send it to Bob, which performs a measurement. Now, this was as written in the abstract of the paper. This demonstrated experimentally that one can transmit one of the three messages, that is one trit, 1.58 bit, by manipulating one of the two entangled particles. So as I have discussed in case of the theoretical protocol by Bennett and Weisner, where they have sent the protocol that they have discussed, where we send 2 bits of classical information from Alice to Bob. Now, experimentally, initially, they have demonstrated only 1.58 bit instead of 2 bit. But this also can show certain quantum advantage. And because you should remember that in case of experiment, they are unable to prepare exactly the singlet state, but this was noisy singlet state. And they use polarization degrees of freedom. And so in that state, the 4 orthogonal states, this singlets and triplets cannot be distinguished exactly. And that is also another problem in this protocol, which possibly I will also touch tomorrow. And so this is the first experimental demonstration of dense code. The next demonstration is by NMR in 1999, where they have used a molecule 1H13C in the molecule which is CHCl3, and in that molecule they used to demonstrate dense coding protocol. So as they said, they demonstrated experimentally via NMR technique 2 bits of information have been transmitted through manipulating one of the maximally entangled state, and this is consistent totally with the original Bennett-Weisner protocol. But as we know, in case of NMR, it's a hard because it's a molecule, and usually here also the hardly the always the state is a noisy state, so it's a arbitrary density matrix, and here the spatial separation is also a problem. But this is of course a demonstration, in some case proof of principle experimental demonstration, how to demonstrate dense coding protocol. The next experiment was done by David Wineland group in US, where it was by 2004 by trapped ion. So trapped ion is one of the experimental frontier where we expect to build several quantum devices like quantum computer and etc. And this is one of the promising candidate physical system where several quantum information protocol have been demonstrated, including quantum dense coding. And so they have used 9 barium plus ion, and they have implemented quantum dense coding on individual atomic qubit with the use of 2 trapped 9 barium plus ion. So they actually trap 2. So here I have shown several atoms to be trapped, but instead they have trapped only 2, and they are entangled that they have shown, and then they perform Bell measurement to distinguish between these 4 operations which encodes these 2 bits of classical information that I have discussed in detail previously. That's exactly the Bennett-Weisner protocol. Now here I just want to mention that this Sergey Harouse and David Wineland group have independently invented and developed groundbreaking method for measuring and manipulating individual particles in trapped ion system in cavity QED, and their groundbreaking work was recognized in 2012 by Nobel Prize in Physics, and so they are kind of experts in how to manipulate and measurement or address individual qubits in trapped ion system. And he has a very nice experiment. Both of them have very nice experiments implementing several quantum information protocol. Probably you will also learn in other quantum lectures in this workshop. And so I just want to tell that these are all protocols in 2004 and so on, but there are several open areas even in this field, which looks like a happy field. But as I said, there are several open questions still people are trying to address. So for example, in 2017, this is a PRL paper where they have shown that how to really implement dense coding protocols by using optical fiber links. And this is important too also for if we really want to build quantum communication network or the dense coding protocols between several senders and the receiver. So this one, as they said, that this is a demonstration of dense coding protocol over optical fiber links. Now this actually has an advantage because they have created a time polarization hyperentanglement, and in this way they actually can have a complete Bell state measurement, which was not possible in the original photon experiment in 1996. So in case of original protocol by Anton Zeilinger, they were unable to perform a exact Bell state measurement. I mean, still in the polarization experiment, they cannot they cannot distinguish 4 Bell states. But to avoid the situation or to overcome the situation, here they have used a clever method. They have created a time polarization hyperentanglement, where by using linear optics and common single photon detector, they can perform a complete Bell state measurement. In that way, they actually reach kind of the capacity of 2 bits of sending classical information in 2017. And so this is one of the breakthrough in recent time, and also there are many experiments where now people are trying to, so all these experiments that I have now showed, these are all experiments where there are only one sender and one receiver, so only involve two parties. But I haven't shown here, but there are several experiments now people are trying where they want to build a dense coding network involving many senders and a single receiver. Some of the experiments I will show tomorrow, on Monday in the next lecture, how they are trying to build the communication network. So with this, I just end my talk. This is the current group of mine who are working. Some of them are extensively working on communication network. And this is the entire QIC group at HRI, although it's a bit old paper, old photo, 2023. And thank you very much for your attention.
Thank you so much, ma'am, for that enriching talk and for sharing your insights with us. We now have a few minutes for the questions from the audience.